Yeah, so like Trace said, so I've been with the Society for coming up 3 years. So I've completed this master's degree, and I hope that the aim of this presentation is to actually give people an insight as to what it's like to be a master's student with the Open University in space science and technology, and also give them a special treat, as it were, about spacecraft sustainability and space system sustainability. And I'll go into a little bit more detail about how that could be possible in the future. And I'll go into more detail about what the kind of cool things that are happening now. But this presentation is basically about my experience at the Open University and the results of my my study, which took an entire year of study. So at the final year of your study with the OU, you do a project, and that project normally takes a whole year to complete. So you don't, no one holds your hand with this. You literally get thrown in the deep end, and everyone thinks that you've got plenty of time when really you don't. It takes a long time and a lot of effort just to nail down a specific title that you want to use, and it'll probably change 5 or 6 times as you're going. But one thing that became clear to me, the more I studied this subject, which is prospects for 3D printing and sustained spaceflight beyond low Earth orbit, was that this is a real thing, and I became more and more passionate about it as I went along. And actually, I found a job working for MDA Space and Robotics at Harwell, which directly related to this, which is what I do now, assembling, integrating and testing spaceflight hardware, which will eventually land on the moon and Mars eventually as well, I suppose. And these are very real things. So this is a very real, serious presentation on how those spaceflight hardware components could be made in the future and are being made right now. So this is the bridge, if you like, between academia and real industry. And I'm hoping that this really gives an insight to people and excites people about the future with our prospects for sustainability in space. There we go. So my introduction. So pictures paint 1,000 words. So I'll start with these pictures on the right here. So if anyone doesn't know the Apollo 11 landing, there's a couple of really good films out. First Man, if anyone's seen that, that's brilliant. And one thing that everyone forgets, and they never ever go into any detail about this because the Americans find it extremely embarrassing, is the fact that some of their spaceflight hardware broke on the surface of the moon. So the picture up here in the top of the screen is the circuit breaker button for the ascent motor in the actual lander module. So what happened is that circuit breaker, Neil Armstrong will push that button, and basically it's the go button for the ascent motor. So without that button, there's no way on Earth that they would ever been able to lift off from the surface of the moon. And unfortunately, for Apollo 11, when they got back into the spacecraft after doing their EVA, their EVA suit was so big that actually they knocked off the switch and broke it, which is absolutely terrifying thing to happen, obviously, because you've got no way of leaving the surface of the moon. However, back then the hardware was very simple. It was literally just a small button, and luckily, the astronauts had plenty of items in the lander, and one of the items was a pen. So they used that pen to do an in situ repair on that spacecraft, basically remove the broken part and use the pen to push the switch to close the contacts to get a good electrical connection so they could leave the surface of the moon. Now, the big problem now with spaceflight is that not a lot of this equipment still exists. A lot of equipment these days is reused because it's reliable and it's good. However, with sustainability now becoming a mainstream thing with SpaceX and big companies like Blue Origin, and they want to reuse this hardware, they're now changing that hardware from old, commercially available off-the-shelf components to more serious, smaller components that you really cannot get to without dedicated tooling or ground support equipment. So it's clear that in the future, if something like this was to happen, you would need to do a repair on the surface of the moon. You may need to manufacture a new part, and that's the reality of it. There's no way of getting around it. If this happened in the future, you may need to make a new part. And this is the real aim of this presentation, is to show you how that could be made. Right. So yeah, the aim of my reports was to use a combination of literature and data to optimize the 3D printing process for sustainable space missions beyond low Earth orbit. The objectives of the work was to gather and evaluate all of the existing data to determine how 3D printed structures behave in space, and determine by literature review how 3D printing can be used sustainably in space, using in-space manufacturing, demonstrates how 3D printing can improve the reliability of mission-critical systems for missions beyond low Earth orbit, and propose an experimental regime for in-situ manufacture and testing. And after a year of work, I did actually achieve most of those goals. And this is how I did it. So another really good story here is the sustainability in space at the moment. So obviously this is the International Space Station. So what a lot of people don't realize is that the International Space Station has got so much hardware. If you think about your house, lots of people have equipment in their house. They've got unused items, all sorts of crap from the past that they never use. The International Space Station is no exception to that rule. So they've actually got up there 1,260 kilograms of corrective maintenance tooling. So that can be things like, nuts, bolts, spanners, general items for use. Preventative maintenance consumables, so things like filters, oils, refrigerants, Kapton tape, aluminium tape, just general items you would find, and that represents nearly 2 tons of equipment. So that's over 3 tons of equipment that is not being used, which could be used for scientific endeavors. And in annual failures, you also have nearly 0.5 ton of spares being used. So when you add all this weight up, the approximate mass of items currently stored on the ISS comes to over 13 tons. So that's a lot of mass. And considering that 1 kilogram, I don't know the exact figure, but 1 kilogram launched to low Earth orbit is in the tens of thousands of US dollars or euros. This is a lot of money, a lot of time, and a lot of wasted space that could be used a lot better. Additionally, there is nearly 18 tons of spares waiting on the ground to be used if there's a failure on the ISS. So that's 17 tons of equipment ready to be launched at a moment's notice if they have a critical failure. So there's an awful lot of mass there that could be used. So the basis of my study was this lady here. Her name's Tracy Prater. We all love the name Tracy as for the society. She's a nice lady. I've sent her plenty of emails about this this subject, 3D printing in space. Every single one of them, she has completely ignored me. She probably thinks that I'm a complete weirdo, a British guy that knows nothing about space or anything like that. So Tracy, if you're watching this, please email me. I feel really, really sad. But now she wrote this paper about 3D printing in space back in 2018, and it's a really good read. You should look it up and have a good read. My research was based on this paper. Now she works doing process monitoring and utility of manufacturing technologies to meet the needs of repair on space missions. So this is the lady who's going to deal with those missions where you're going to land on the moon and there's going to be a critical failure, and Tracy's the person everyone's going to be pointing their finger at and saying, I want my new parts because I broke it. And Tracy's going to say to them, no problem, I will 3D print you a part and you're going to have it in 30 minutes. So that's Tracy. So she's a very important lady, and she's very good. So what is 3D printing then? So 3D printing is commonly known as additive manufacturing. It's called additive manufacturing because you're not subtracting anything. Subtractive manufacturing is when you remove items. So let's say casting, for example. You cast a bonnet of a car by placing it in a die, and you get your material and you shave the ends off, and those ends that are shaved off are then recycled and reused, hopefully, or not in some cases. So additive manufacturing, you're adding material to something, but subtractive, you're removing material. So for space, you need to use additive manufacturing because there is just not there's no hope that you can ever use a subtractive method because it's so wasteful. So these two pictures you can see here are from Tracy's study in 3D printing. So it's a lattice work of material, and it's extruded from the 3D printer in a line, and it generates layers and layers of 3D printed material. And that's what these lines are under a microscope. So it prints these layers, fine layers of fiber, and it will make a mesh, just like a cotton shirt, basically, a very fine mesh. And eventually, if you get enough layers, you get a very strong material. And the pictures in the middle, they represent the left picture in the middle that you can see, one that says G001. That one is a ground sample, one that was printed on the ground. And then the one on the right that says flight 001C, that one was 3D printed on the International Space Station in 2015. And as you can see, there are some subtle differences. The one on the right is more brittle, and the lines are a lot straighter. The one on the left doesn't look as brittle, but there are some fiber slump, which could be explained due to gravity. And the one on the right, obviously, the lines are more straight. So they suspected that actually those lines will be caused by reduced gravity. So I said to myself, well, why don't I test this? Why don't I test this theory? In order to test this theory, there's a couple of things you've got to know about 3D printing. So the setup parameters are really important. And the first time NASA did this on the International Space Station, they completely messed it up. They did one test, and then they tried to compare it to another test, and it all went wrong because the test parameters they used, they didn't record. So it wasn't science at all. They just wanted to see if it would work. And now they all know that actually the 3D print is all about the parameters. 3D printing is an art. It's less of a science, more of an art. You trial by iteration every time. So this graph you can see here is dynamic viscosity versus temperature. So as the temperature increases, the viscosity it decreases, obviously, so it becomes more fluid. And that's really important for 3D printing, and it's really important for applications in microgravity as well, because if you reduce the temperature slightly, you can make it more viscous. And if you make it more viscous, then you're reducing the impact of gravity. So a good analogy to use this, it's fine. You can make a sandcastle on a beach in the UK or anywhere. Hopefully not the UK because it's too cold. But if you 3D print, if you make a sandcastle on the beach, most of the time, if you get the good composition right and of water and sand, it will be a nice solid structure. And if someone said to you, could I make a sandcastle on the ceiling in my bedroom above my parents' bed and be 100% confident that sandcastle will not fall down, then everyone's happy. But unfortunately, if you try to do that, obviously it's not going to hold, it's going to fall down. So if you make it stronger by reducing the temperature, you might have more of a chance. So it's a very fine balancing technique. And the ultimate goal of 3D printing is to find that balance and automate it. And you can do that by studying it, which is what I did. So with all things 3D printing, there has to be a way to recycle it. In an ideal world, your spacecraft would recycle absolutely everything. So in the example here, we have something called a refabricator. So this one was sent to the International Space Station. It basically 3D prints your parts, whatever part that may be, and then you can put it back into the refabricator and then turn it back into feedstock. So it crosses up like a coffee machine, and then the 3D print, then the those small flakes of 3D printed material, plastics. They get heated up and they get turned back into extrusion material, ready for 3D printing again. So you can reuse some of those parts again and again. So, and that has been proved. Unfortunately, the data is not available at the moment. I have asked Tracy, but as you know, she's not replied to me, and I can't find this data anywhere. But it is a thing that's up there, and all the data suggests that it does actually work. So if you're on your long duration space flight to Mars, for example, all of the cost saving that you've done by having your 3D printed part, if you need a spanner to do up some nuts and bolts, you can 3D print your spanner, but then the spanner might be useless for years. And you don't want to keep it useless for years. You might want to say, right, I want to turn it back into 3D printed material again so I can reuse it for something else that I need. And that's exactly what this is for. And it's very, very useful. Unfortunately, the data I can't find anywhere at the moment. So what I did then, I reproduced the data from NASA. So I got the CAD file, the original CAD file that NASA used, which are these two pictures here. So F024, F026, they are the sample numbers of the parts that I've reproduced. So the cylindrical shaped one, that one is a compressive sample, and the right one is a tensile sample. So my ones that I've made are on the left. So sample D1A, that's a replica of the NASA printed part, and the one in the center left is a replica of the compressive part. And I made 66 of these samples in total and tested them in various different ways. So what I wanted to see was, do my stress tests that I'm going to do on these parts, do they agree with what NASA have said? So I needed a good baseline for my science that I wanted to do. So my initial test was to see if these parts were indeed printed at the same quality and standard as NASA said. So so I went through these tests. So I had ultimate tensile stress, elastic modulus, and elongation to failure, so where it snaps basically. So elongation was measured with a extension meter. The temperature was 23.8 degrees Celsius, and the ambient pressure was sea level pressure basically. And it was pulled at a speed of 5 millimeters a minute to match the NASA's 0.2 inches per minute speed. So the test parameters were monitored very closely. I think when they tested theirs, the temperature was slightly lower. I think it's 22 degrees, but I couldn't get it perfect. It was very hot when I did this over the summer. Then I did the compressive tests. So I 3D printed the compressive samples, and then I tested those the same way. So the top picture there you can see is me using a stress tester at Harwell campus in the United Kingdom, and a very expensive machine. And the green item you can see there is the item that measured the elongation as it was on its way to failure. The bottom picture is the compressive stress test machine. It was excessive because the part I was trying to break was very small. So again, this measured at Harwell campus in the UK, and I got some very interesting results. So here's my results. I think you can ignore that chart on the right because it's completely out of range. So just look at the table here. So NASA, the row, the two first rows there, those are the NASA samples that were printed. And then the last three samples, sample A1, A2, and A3, they're my samples. And as you can see, they're not too far away from the phase 1 ground samples that NASA made. There is a bit of a anomaly there with the phase 1 samples from NASA, and I think that's just a test setup issue, which is represented by the massively out of range phase 1 bar there. So yeah, so I had a good baseline measurement, and it confirmed actually that my tests were good, and I was very pleased with that. So from that point, I had time to then carry on with my testing. So then I started to get a bit more excited about what I was going to do. So I decided to get these printed samples, put them under a microscope. So this is what I saw. So obviously the blue ones at the top there, they're the compressive samples before they were tested to failure, because they're a complete mess under a microscope. There's no point even looking at them. So as you can see, the compressor samples are a lot neater than the tensile samples. The fibers are quite neatly placed together. The scale there is about 100 micrometers for the width of the bead. So it's quite small, but not too small. The sample numbers, they're basically the extrusion tip distance on the base of the plates that's being printed. Sample A1A, the bottom left one there, you can see that the beads look quite elongated, and that's probably just due to the placement of the fibers onto the extruded bed. So then I measured the deviation from the CAD, so the original CAD drawing, how far that the 3D printed part was measured, and then it was the deviation in size was shown here. So it's pretty close. This is in percentage, so they're pretty close. They're all approximately less than 1% within the same as the CAD. There is slight differences between the compressive and tensile stress samples, but you know what? They're pretty close, and they're consistent with the NASA samples, which is the ones I wanted to really see. So I knew I had a really good baseline to start with here. So I'm sure that all of you are aware of the how the Russians got away with not making a pen for space. They decided to use a pencil. So what's I've come up with here was quite a good solution to test 3D printing at reduced gravity, which was to turn the 3D printer upside down and try and do that. And luckily, this 3D printer here, you can see, that uses jack screws to screw the bed in, so it doesn't necessarily matter which way around you 3D print it, because it's not affected by its position. So I gave it a go. As you can see on the bottom right there, it didn't quite come out well the first time I did it. So the extruded material came out onto the extruder tip, and it just made a big mess. So the first thing I realized was getting a good adhesion to the bed was really important. And the purpose of this was to show that is there any difference between printing at 1G or any other type of gravity, reduced gravity, -1G or whatever. And there was no other data I could find anywhere. So I went ahead and decided to just try and print something upside down. And if you go on YouTube, you can see people having to go at this, and most people are quite successful. But the difference is, for my master's degree, I got some really good data on this. And here it is. That's the data that I got. So obviously, it's the first time that this data has been collected. I'm sharing it with you now. I tested at reduced layer heights, higher temperatures, and lower speeds to see if I could get a good adhesion onto the bed. Once it's stuck onto the extrusion bed, which is the plate that you 3D print items on, once it was stuck firmly on there, I had no problems at all. So I then played around with reducing the layer height. That's the distance between the extrusion head and the plate, and printing at a higher temperature, because as you know, if you print at a higher temperature, your viscosity goes down. So I had to go at that. And I tried printing at a lower speed just to get some slightly more adhesion from the extruded parts, extruded material, sorry. Deviation with CAD on the right there. So what the distance is between the edges of the parts being manufactured compared to CAD, and the average bead width down there as well on the bottom left. So that's how wide the extruded bead is. And as you can see, there's a big difference there for higher temperature, and that's probably because of the change in viscosity. And that's really important for spaceflight, because as all you space engineers know, temperature varies widely for space applications. So that is showing that actually changes in temperature are very important, and I'll explain why later in this presentation. There's the optical analysis. So printing upside down was very challenging, and as you can see, the fibers are completely all over the place. The width of the beads being produced is completely random. and skewed. So they're no longer straight lines, they're curved. And this could be for a number of reasons, most likely due to negative gravity slump. So as Tracy said in her research, it could be down to a gravity slump. Well, there's evidence here of something going on in the same axis direction as the printed part. So this is direct evidence to show that actually gravity does have some sort of influence on 3D printing, because I'm showing slumping in the opposite direction now. And what that's doing is that's stretching out the fibers. So the bottom picture there, you can see B1D. So you can see a stretch, and it's pulling the fibers apart, which is actually reducing some of the tensile compressive stress on that part, and also some evidence of brittleness as well. Then I went a step further and I decided to 3D print things at reduced pressure. So this is a test I didn't do at Harwell. I actually did this somewhere I'm not prepared to disclose, because what I did here was slightly risky. I took a 3D printer and I put it in a vacuum chamber and I decided to see if it would survive. But this 3D printer was quite expensive. Didn't belong to my company. It belonged to someone else, a good friend, shall we say, which survived actually. So there's the results of it. So I managed to 3D print and at normal pressure, ambient pressure, and then slowly reduce the pressure down to 55 kPa. And that's a really important figure, because 55 kPa is the expected pressure that will be the lowest possible pressure that will be used for human exploration on Lunar Gateway. So that's obviously really important, because if you're going to 3D print parts on Lunar Gateway, then you need to know if your pressure, the drop in pressure, is going to affect anything. So I gave it a go. And what I saw with this is very interesting. So printing at a lower pressure, as you can see, the ultimate tensile strength is the lowest at 55 kPa. The elastic modulus is the lowest. Compressive stress test at 20% strain is again the lowest. And the compressive yield stress in megapascals, that is again, that is the lowest. And compressive modulus, again, the lowest. So there's some really strong evidence there that actually 3D printing parts at a lower pressure reduces the mechanical strength of your parts. And then again, you've got your deviation from CAD and your bead width. So I'm seeing here my bead width is reduced, and I actually expected it to expand, because when you put things in a lower pressure, they tend to expand. But in this case, for some reason, the bead width was less. There's the optical analysis. So quite a lot of distortion there. It looks like there's been some outgassing going on, and potentially what's happened here is some of the gases in the 3D printed part, as it's been printing, have escaped, and the total volume that's being used by that part in the extruded material has reduced. So the volume of material is reduced because it's outgassed slightly. And what that may have done is just distorted the part and made it slightly more brittle. As you can see from C2E, the compressive one in the middle there, it looks very brittle, and it looks like something that's seriously gone wrong, which is very interesting, because that's in the exact same spot each time for each sample, which is dead center in the middle of the part. So printing with COTS, recycled material. So COTS is commercially available off-the-shelf parts. So you can 3D print with recycled material as well. So I thought, why don't I give this a go? Because there's so much trash on the International Space Station. I thought, can we reuse some of this and turn it into 3D printed material? And they do that already with a refabricator. So why not give it a go on Earth and see what happens? And there's the results. So the ultimate tensile stress from 100% recycled material that's available commercially was quite low. And the 50% recycled material that is a lot higher, and it's quite comparable actually, 21.83, the ultimate tensile strength, to a normal 3D printed part with new material. So then the question has to be raised, is it better to actually 3D print with 50% recycled material or 100% recycled material? So it depends what your application is. If you need something that is flight critical for safety reasons, you may just go with the 50% recycled if you're running out on the way to Mars or whatever. But that's showing there that if you use 50% recycled material, sorry, 100% recycled material, then you run the risk of your part breaking. And that's just because it's more brittle and it's obviously been used. It's lost some of that strength. It's comparable to old car tires. You know, once they've been used a few times, exposed to a lot of heat and radiation from the sun, they start to crack. And that's very similar to what we're seeing here with the 3D printed materials that are being reused again and again. They start to become more brittle, crack, and they become more susceptible to damage, which is shown there by the stress measurements. Interesting, the average bead width for 50% recycled material is 101.4 and 100% recycled is 98. So there's a bit of a difference there. The recycled material is slightly bigger actually than what we'd expect from the 3D printed machine, which should produce beads at 100 micrometers. There's the optical analysis. So this is a really interesting one. D2B is a combination of 50% recycled material, is 50% recycled. The white material is actually, it's good new material, and the red, or it looks more pink there, is the older material that's been reused. So as you can see, it's coming out in globules, and it's definitely not straight. D1A is very straight, but D1A is new material. And it's coming out perfectly. But D2A, the combined material, it's formed in a way so that the microstructure is linked together tightly, but actually looking at it under a microscope, it's questionable whether or not that's a good material to use. But the stress of the material proves actually that it is quite good to use. So it's quite interesting to see how that works under a microscope. And if any future study I do, I'll look into this in more depth. But this is quite interesting, really. So how does this all come together then? So how could I use this information to my advantage for my employment and for the future of human spaceflight? So I was in work and I was thinking, right, okay, I'm doing a project, and this project involves a 25-way D-sub connector, which is used for a genuine space mission, which I can't mention here, but this connector it will go to space eventually. And as I was making it, one of the clips broke, and I thought to myself, well, if the clip can break here on Earth, then it might break in space. So why not come up with a 3D printed CAD file and see if I could make one, 3D print one, so that if something goes wrong in the future, on your way to Mars or any other planet in the solar system, you can replace it if you need it, rather than wrapping it up in duct tape, which seems to be what a lot of astronauts have to do, which is not sustainable. So I created a CAD file and I 3D printed it. And as I 3D printed this part, I thought to myself, what am I going to do with the screws that are on it? Because there's two screws, as you can see there in the picture on the blue 3D printed part. Sorry, the blue connector is the 3D printed part, and the left side is the original that broke. So I reused the screws. So I iterated on the design, and I thought, well, I can reuse some of these parts. You know, otherwise they're going to get wasted. They're going to end up stored, using up valuable space. So then the real gold came out. I realized I could 3D print a part and reuse most of the parts that's from that component. And then the ultimate icing on the cake is that the plastic that was used originally can be put in the refabricator and then turned into a 3D printed part eventually. So you end up with 100% reusability for this part. So if this was it is a genuine space mission, but if this broke in space and you had a 3D printer, you could repair it and completely replace the entire back shell of this connector with zero waste, nothing at all. It's all completely reused. Every single gram of material completely reused, which is the ultimate goal of 100% sustainability. Now, the problem is that you need to certify this for spaceflight. And that's what I did. I went to NASA and ESA, and I decided to go with the NASA standards to excite people because of SLS and other means. And I decided to certify this for spaceflight. And here we go. This is the acceptance test criteria for this thing to be able to fly to space. So I did a lot of this testing already. So the loads of the environment has to be well-defined, bounded loads environment. So well-defined or bounded load environment is defined. Blah, blah, blah. You needed your ultimate tensile, ultimate strength test, your yield stress, and your and other things. Basically, your basic mechanical tests, which I had already done. And a lot of this stuff is not applicable because it's not going through a high cycle fatigue. It's not going to be put under any stress. It's going to be built, connected, and occasionally it may be demated from the components, from the parts, but it's unlikely. So a lot of it was not applicable. And then suddenly I thought, well, okay, if it's not applicable because it's just a connector, then yeah, it could be used. And there it is. So there's the that's the criteria there. It's MSFC standard 3716 assessment criteria for additive manufacturing risk and assessment for structural demand. It's a NASA standard. So 3D printing a lunar base. I decided I was bored one day and decided to 3D print a structure from the moon. Right? This 3D printed structure here with, I think that's a Intuitive Machines lander, and you know, give it a go. So can we 3D print a base on the moon? That was my next question. I decided to do a Delphi study. A Delphi study is when you ask lots of people, professionals, questions. You give them a specific question. When will we be able to 3D print a moon base? And a lot of those professionals will come back to you and say 2030 or 2040 or 2050 or 2100. And then you just get the average of that, the mean, and then that will most of the time be the day when the year when you'll have a base on the moon, which has been proved before, and it's pretty close. So I did a Delphi survey, and I found out that actually a 3D printed moon colony may potentially be possible in 2042. So that's the baseline. So can you 3D print on the moon? So future colonization of the moon will require large-scale 3D printing of habitable buildings. So this is an attempt by an American company. So as you can see, they've got a few elements of my study in this as well. So they're 3D printing walls. They're not hollow. They are hollow walls. They're hollow because you need to fill it with some kind of insulating material, just like you do a normal house. And the thing that's missing from this this picture is the angled roof, because this company that designed this didn't know how to do it, because obviously the gravity on Earth is much higher than the moon. So there's no way you could demonstrate how to build an angled surface on Earth, because it may not work, because on the moon the gravity is less. So that was something to consider. You can notice also that it's inside a tented enclosure, and the reason for this is due to your print parameters. So when you 3D print something, you have to keep the parameters of your print the same. So if the temperature changes, your entire print changes as well. So if we're going to 3D print a structure on the surface of the moon, then you have to put up some kind of enclosure around that robotic operation to keep the parameters the same, and then potentially pressurize that environment very, very slightly to get the exact parameters you need for an optimal print. It may be possible to use an inflatable structure for the center and then 3D print around that structure to get your angled roof. A lot of time you think, well, do you need an angled roof? Well, actually, yes, because it's a stronger structure than a rectangular shaped one. So yes, you do need a rectangular roof, and it will be easier on the moon if the parameters are kept, print parameters are kept stable. So printing inside a crater might be advantageous on the lunar South Pole, potentially, but that depends on the lunar regolith you're using. So there's a few things to think about before we can say, yes, we're going to 3D print a structure on the surface of the moon. And the key thing with this picture is it's not humans that are 3D printing this. They're completely away from this at all. So it's all robotic. It's a completely robotic operation. So if we have a robotic operation, we need to monitor that as humans. So it's semi-autonomous. And we're going to do that with scanning techniques. One of the key scanning techniques that the space industry uses is LiDAR, which works the same way as radar, except you use laser pulses. And here we have a setup for a spacecraft. I'm not sure which one it is, but you have a laser, and you use the simple formula D = CT over 2, which is your distance is the speed of light times the time divided by 2, because you've got your light pulse going down to your structure that you want to scan, and you have the return pulse as well. That's why it's over 2. LiDAR, it can be very, very accurate, and you can scan a surface very easily. And scanning is very, very important for scanning a structure. And when you're landing on the moon, you may want to use LiDAR, because radar can be quite temperamental, and so can LiDAR. But LiDAR is becoming more of a thing with spacecraft. It uses something called an avalanche photodiode, which is in the center of the operation. Basically, the laser pulse gets returned, and it goes to this avalanche photodiode, APD, and it gets a signal, and it records it, and you end up with your data, and you can build up a CAD file or a CSV file in Python to build up your structure. So very useful. The next one is structured light scanning system. So this looks very creepy because it looks like it's got 2 eyes. And it's got these 2 cameras because it works very similar to how a human looks at something and develops their depth perception. So it uses 2 cameras to look at depth, which could be used alongside LiDAR to scan your surface. And why would you want to scan it? Well, you want to scan it because when you're printing it, you want to know that your item that's being printed, if it's a moon colony or whatever, you want to know that what's coming out of the extrusion nozzle is what you hope it's going to be. If you leave a robotic system there just to print on its own and rely on that, because it's more of an art to 3D print, you're not going to know 100% that it's right. So you need to scan it. And on top of that as well, you need to scan the printed material after you've manufactured it for any damage that might be occurred due to micrometeoroids or the sun causing expansion and cracking and so forth. So every single structure that will be 3D printed on the moon should be scanned. And the scanner that made the thing in the first place should routinely scan that structure, because if it's there, you might as well keep it there or reuse it. And it's great because you do need to do some non-destructive testing, NDT, on those structures every year anyway. So let's keep our robot there, and let's keep it monitoring the structure that's being built. So in conclusion then, so I looked at some of the NASA samples. I compared them to the samples I had. I got a good baseline measurement, and I'm very happy about that. I got my 3D printed samples. I tried a few new things, and I came up with some really good conclusions about how we could 3D print things on the moon and far out into the solar system. And I've had the privilege to actually work for a company at Harwell in Oxfordshire that actually makes some of these parts, and they use a 3D printer quite regularly for mainly for ground support equipment for spacecraft, and also some for actual spacecraft. So it's a very real thing, and it's based on design iteration and continuous development of this technology. And I see that actually this technology will be the driving factor as to whether or not we could have a colony on the surface of the moon. And that's my belief. And yeah, that's my presentation. And if anyone's got any questions they'd like to ask me based on the presentation, then go ahead.